Can you guys see that whiteboard?
Yeah.
Okay. So, batteries have been around for a lot longer than you probably think they have. Although they didn't have much function for the general public, they were mostly things that scientists used to study matter. And then finally, people were able to create things that were at least useful in some manner. And the first two types of diagrams that we have for batteries, they're basically the same kind of diagram. Two different people created the diagrams at about the same time. And so they're either called a galvanic cell or they're called a voltaic cell. You might not recognize the galvanic portions. Hey, please stop. But you most likely know volta from volts. And so the way they describe the way the battery would look, or their first batteries. Let's see, go maybe black. Then maybe some yellow. Some blue. Do like that. And then let's say, how about we'll do, how about that? Sorry for my poor straight lines. And then we'll do a wire.
All I have is a white screen. Are you drawing something?
Oh, yes. You can't see me drawing.
No.
How about you, Becca?
Can't see anything, just a white screen.
Okay. How about that?
There you go. That's better.
Okay. Sorry. Right, eraser. Why is the eraser not erasing? There we go.
It looks like I redrew the picture that's on page 335.
Yeah. Close. Almost the same thing. Okay, so the way almost all batteries work is you have two separate metals. Can you guys think of any names for any batteries?
Penelope.
Alkaline?
Okay,
Wait.
an alkaline battery, that's definitely a type of battery. Those are generally non-rechargeable batteries, like your regular Duracell or Energizer or something like that. Any other names?
Are there zinc batteries?
Those alkaline batteries have zinc in them, for sure.
Lead acid?
Yeah, where do you find the lead acid battery?
Looks like a car.
Yeah, the lead acid battery is your car battery. Absolutely. Any other names of batteries? How about one you carry around with you most of the time during the day?
Lithium?
Yep. So then there's also a lithium-ion battery. With these, and then other ones like nickel, like a nickel metal hydride. Those are traditionally the batteries that people had that were rechargeable. And then there's a nickel cadmium battery that Toyota has been using for, I don't know, 12, 15 years, however long the Prius has been around. And that's the battery they use for their electric and hybrid cars. So what you need is electrons to flow. And that's pretty much what a battery does. The electrons flow from a place who is willing to give them to some other place. And so what I mean by place is you usually have a metal that's willing to give electrons to another metal but that metal has to be able to accept them, and the first metal needs to be able to have them. So what that means is, do we remember any of the oxidation state for metals? Like if you look on the periodic table, could you tell me the oxidation state for like lithium or magnesium? Since lithium is in group 1, if it reacts, it becomes lithium with a plus charge because it lost 1 electron. And so everybody in that first column does that. And if I'm magnesium, since I'm in column 2, what I tend to do is become magnesium with a plus charge because I just gave away 2 electrons. So those 2 electrons go off and go do something, or this 1 electron goes off and does something. And what happens is you're left behind with this magnesium or this lithium that are missing electrons. For us, we would typically call that rusting, but in actuality, it's oxidation. That's what a chemist would say has happened to that. So you will have one metal that donates electrons and another metal that accepts electrons. So in this case, we've got magnesium over here, and we've got copper over here. But I haven't completely filled out this table, and so what I also need to put down in here is that inside of the solution here, there's going to be some magnesium that's already got a plus charge, and there's probably something like nitrates that are floating around. Nitrates because they're always soluble. You don't have to worry about them making a precipitate. And then over here we're going to have coppers. Oh, I should undo that. Put that in orange. Over here we've got copper that's got a +2 charge, and we'll just put nitrates in here because it doesn't really matter. Okay, so metals can have a charge of 0, and so if they're metals in their elemental state, like here, this lithium's charge is 0 and this magnesium's charge is 0, and these guys' charges are +1 and +2. If I'm a copper and I haven't done anything yet, then my charge is 0. And when I do something, my charge will most likely be +2. Doesn't have to be +2, but it's most likely that I gave away 2 electrons to go to someplace else. Okay, so what is going to happen here is the magnesium is going to be giving electrons away to the copper side, but the magnesium can't give electrons to copper directly, to copper metal, because this guy's charge is 0, and what would its charge be if this copper tried to gain 2 electrons? If this magnesium tried to give 2 electrons to that copper, what would the copper's charge be?
-2.
Yeah, and metals can't be negative. They can be 0 and they can have a positive charge, but they can't have a negative charge. So copper metal can't actually accept any electrons. But in this drawing that we have up here and the drawing that's in the book, there's some copper right here. So why does this copper have a +2 charge?
So that it can accept the negative charge?
Okay, but the reason it's +2 is because it lost 2 electrons, okay? And the magnesium over here, this magnesium that's in this bar of magnesium is willing to send over 2 electrons. And when it does, it goes down this solid copper bar, and then there's 2 electrons right here that are negatively charged. And then this thing right here becomes copper metal. It attaches itself to the bar. So tell me about, what do you think's happening to this copper bar right here?
Marginally growing bigger?
Yep, it's getting bigger because copper is attaching itself to it. But on this other side over here, this magnesium did this right here. So when it loses 2 electrons, it can't be a solid anymore, and it goes into the solution. So what's happening to the magnesium bar?
It's shrinking.
Absolutely. So can you tell me one way a battery could go dead?
The magnesium just is all used up, it's gone.
Yep, that's exactly right. It gets all used up. Is there another way that you can think of that the battery would go dead?
Too much copper?
No, not too much copper. But what if this copper that's aqueous, that's in the solution, what if you, all of these coppers that are +2 have all accepted 2 electrons? Then there's nowhere for the electrons to go.
Yeah.
And that battery just stops working. Okay, so what's this thing in the middle for? It's called a salt bridge, but it has a really important function.
It carries ions?
Yes.
That's what the picture in the book says.
Yep. So when this magnesium gives 2 electrons and it goes this direction, what happens to the charge of this entire container? It lost 2 negatives, so the whole container now would be +2 charge. Okay, does that make sense? It gave away 2 negatives and it became +2. So you can't have that. That's not allowable. All the charges have to be exactly the same at all times. So if up here in this container we had something like, I don't know, sodium, just regular old table salt that's aqueous, that's dissolved, every time an electron leaves this container and goes this way, one of these sodiums goes down into the container.
Keeping it balanced.
Keeping it balanced. Actually, I just messed that up. Sorry, that was completely backwards. Let me undo all of that. Okay, so what would happen every time a negative charge left, the chlorine would go in and replace the negative charge, and it would be a chlorine with a -1 charge. But now electrons are coming over to this side, and this side where the copper is becoming negative. So then the sodiums come down the tube and they go out here, and then the sodiums are on this side, so they cancel out that charge. So both containers end up having a neutral charge. That salt bridge, that's really just looks like a test tube that's open on both ends, and it's kind of in a U shape, and that yellow is supposed to signify something like cotton balls stuffed in the ends. So when you flip it over, it doesn't all dump out. So why do we build these things? Why do we build batteries?
So we have power for things?
Okay. So how do we utilize that? So the electrons come out, they're going this way, and here I put something like a phone. So what we do is we make the electrons do something for us on their way over to giving the electrons to the copper. Does that make sense?
Yes.
So our whole function is to make the electrons go someplace that they want to go, and along the way they do something for us. I'm sure you've like driven to the Dalles or driven to Hood River at some point, and someone's like, "Hey, while you're going there, can you stop by the post office, or can you stop by the grocery store?" So they're getting you to do something while you're doing something you were going to do anyway. Okay, so how did I know that the copper was going to be the one that accepted the electrons and the magnesium was going to be the one that donated the electrons? We actually had to test all the metals. And when I say we, I mean humans. Tested all the metals and then checked them against each other to figure out which metals were the ones that would accept electrons and which ones were the ones that would be donating the electrons. And in this book, sorry, I'm looking for the page that gives you the lists, and it's got to be in here. Still looking. Huh. All right. Maybe it's in the appendix. Let's see. Glossary. Extra question answers. Index. Appendix 1, Appendix 2, Appendix 3. Cool, it's not here. So I'm looking for something called an oxidation table or an activity series. Do either of you guys see it? Yeah, totally in the wrong chapter. There we go.
What's it called again?
It's either an activity series or an oxidation table. That's very peculiar. Yeah. All right. Nada. Let me find one. Just a sec. I'll stop sharing that. And I'll come in here. Here. Let's see. It's 23. Electrochem. Okay, can you guys see this thing on the right-hand side that says element and then oxidation reaction?
Yep.
So what this does for you is it says who's ever higher on the list is willing to give electrons to anybody who's lower on the list. Okay? So there's that. We talked about batteries early, and so there's the lithium battery. And we said something about zinc being in batteries and cadmium and nickel. All of those things are metals that are typically used in batteries, and it's showing you what happens. Like the lithium gives away an electron, or the barium gives away 2 electrons, or the aluminum gives away 3 electrons. What do you notice at the bottom of the table?
Heavier metals are the better conductors. Ish.
No, it's not about conduction. The stuff at the top of the list is more easily rusted, and the stuff at the bottom of the list is less easily rusted. And does that make sense based off of those things at the bottom?
Yeah, you don't really see gold rusted.
Right. I mean, the whole reason that gold is used as jewelry and used as money is because it doesn't rust. You wouldn't give anybody a piece of zinc as a coin because after a week there wouldn't be any of it left. It would just rust away. So gold and platinum and silver and copper, those are all money. I mean, the copper, obviously, penny, any penny before 1982 is solid copper. So you can see that little note on the left-hand side. It says will not dissolve in simple acids. So that means if you have acids on your fingers, and so when you touch those metals will not dissolve with them. If you dropped one of those metals into like a can of Coke or into like tomato sauce, then it wouldn't dissolve. But if you dropped any of the other ones that are above that, then they would dissolve. Absolutely. If you dropped when would you have access? Just like an iron nail. If you put an iron nail into a can of Coke and came back the next day, it wouldn't be there anymore. It would be completely dissolved because a can of Coke has a whole bunch of acids in it. The funny thing about what you said was it was probably 15 or 20 years ago. A guy claimed to have found a mouse inside of a can of Mountain Dew, and the defense for whoever owns Mountain Dew said to the judge, there's no way that mouse was in that can because the can was bottled on this day, and that guy says he found it on this day, and if you put a mouse inside that can, there'd be nothing left of it. It would be completely dissolved. It would be goo. And so the guy obviously just threw a lie or like killed a mouse and said that it was in the can after probably soaking it in some Mountain Dew. So there's that. If you ever find a mouse in your can of Coke or whatever, it was just bottled, so at least it's fresh.
Yum.
Yeah.
Well, on that same subject, when I was in high school forever ago, one of the kids in one of my biology classes, or I guess it was probably chemistry, for his big project he had to do at the end of the year, his dad was a dentist and he had his dad keep teeth and he soaked them in Coke. And he
Yeah.
was like, this soaked for a day, this soaked for a week, this, and it was like, there
Gotcha.
was left at the end. It was pretty gross.
Yeah. So bad parents will give their kids soda in a bottle and then just let them drink on it, including fall asleep with it. So what do you think happens to their mouths?
They get bottle rot.
Yep, they don't have any teeth at all. They're little kids who are waiting until they're 7, 8, 9 years old to get some teeth because their teeth rotted out when they were very young, still bottling. And so people think, oh, well, all right, so I never gave my kid Coke, but I put Pedialyte in there, or I put Gatorade in there, or I put apple juice in there. All of those things are just as bad. Apple juice and orange juice and all the juices, they are as bad as cola or 7-Up or something like that is for your kids because they've got so much acid in them and there's so much sugar in them. There is zero difference between OJ and a can of Coke as far as nutritional value because the amount of vitamin C in that is minuscule. So juice bad. Okay, so let's look at this a little bit more. You guys can see the whiteboard again, right?
Yes.
Okay.
Yep.
All right. So in this particular reaction here, what we had was the metal magnesium giving electrons to the ion copper, and so the way we would talk about that is just what we wrote before, magnesium plus 2 charge plus 2 electrons. So this thing would end up becoming aqueous, and it started off as a solid, and its oxidation state was 0. And then the copper started off as a copper plus 2 that was aqueous, and then I added 2 electrons to it, and it became copper that was a solid. These reactions have the same number of electrons, so you just cancel them out. And then what you could do is on one of those oxidation tables that I showed you, they have another form where they tell you what the voltages are. So this little half reaction would generate a certain amount of voltage, and then this little half reaction would generate a certain amount of voltage, and then you add them up, and then that would tell you what the total voltage of the battery would be. And this battery is actually not a very good battery. Oh wait, no, maybe it's not terrible. So this guy would be, let's see, let me scroll down here. So the magnesium is 2.38 volts and the copper is 0.34 volts. So that would be 2.34 volts, and then this one here was 0.34 volts. And so we end up with 2.68 total volts. That's actually fairly powerful battery, even though it doesn't sound very powerful. These batteries that you guys normally buy, the AA batteries and the AAA batteries and whatnot, do we know what those voltages are?
1.5?
They are 1.5 volts. When electronics were initially conceived, they needed to have at least 5 volts to run, and since then we've been able to get it down to about 3 volts, and some small devices we've been able to get it down to 1.5 volts. So the remote control that you guys use for your television, how many batteries does it have in it?
4?
It has four?
Yeah.
Yeah, they probably have two. And the interesting thing about those batteries is when you put them in, you always have to be aware of how you put them in, right?
Mm-hmm.
Yep.
So if these are AA batteries, and the AA batteries have a voltage of 1.5 volts, your remote control needs 3 volts to run. And so the way it works is the electrons will leave here, go into here, and then go off to the device. And then the electricity will come back here. So what happens is the electrons run through here and they get 1.5 volts. And then they go into the top of the next battery and they run through here. And now they get another 1.5 volts for a total of 3 volts. Does that make sense?
Yep.
That's why you have to flip them over. And if you put them in with the same orientation, there's no way it's going to work. Because what will end up happening is one battery is trying to push electrons with 1.5 volts that direction, and the other battery is trying to push electrons 1.5 volts with the other direction. So they cancel out and nothing occurs. So do either of you guys have those TI, like a TI-84 or a TI-89 calculator?
Yeah.
So those guys have 4 batteries in them. So what voltage will those batteries generate?
6.
Yep. Each one is 1.5, so you get up to 6 volts. So those calculators need 5 volts to run, and they're getting 6 volts, and so that's plenty for them to do their job. In terms of the names of what's happening here, this process, when a metal loses an electron, we call that oxidation. And when a metal gains electrons, we call that reduction. Let's look at the reduction one first. Does that make sense? What happened to the charge on the copper?
It went down to 0.
So its charge was reduced, right?
Mm-hmm.
So that's how you know which one was reduced. And then the other one is the one that was oxidized. So anybody have any idea why the term for this is called oxidation? What does it sound like must be around?
Oxygen.
Oxygen, yes. So why do they call it oxygen or oxidation when we just saw a reaction and there was no oxygen around? The reason is because when chemists were looking at magnesium and it would rust, they would always find it like this. So the magnesium lost its electrons and it lost it to the oxygen. The oxygen would take those electrons away from it. So they coined that process of a metal losing electrons. They called that oxidation. Why do you think the oxygen was always the one that was there reacting with the metal?
Because oxygen has a -2 charge?
Nope, not that it has a -2 charge. First off, it's 20% of your atmosphere, so you just can't get away from it. So it's always around. And then the other reason is it has an electronegativity number of 3.5. Right next to it, fluorine has an electronegativity number of 4. These are the two biggest numbers. And what electronegativity means, we talked about this on chapter 2, is the atom's ability to take electrons. So oxygen and fluorine are the two best atoms on the table at taking electrons. So when the oxygen sees this magnesium, it just takes 2 electrons away from it. And then it makes this compound right here. The reason we don't call it fluoridation, even though that fluorine is better at doing this than oxygen is there isn't any fluorine in the atmosphere. So they never noticed it. It does do a better job than oxygen does, but it doesn't. It's not around, so it didn't get to be called that. it's a little misleading because when somebody says oxidation, it makes it out to sound like oxygen is present. But in actuality, what it means is that thing, most likely metal, just lost 2 electrons. Or, sorry, just lost electrons. Could be 2, could be 1, whatever. Does that make sense?
Yep.
Okay. What else we want to talk about? There's a bunch of stuff about solar cells in here, and there's some stuff about fuel cells.
The comic was pretty great.
The one at the beginning?
Yeah.
Yeah, that is good. Makes me think of that movie, Batteries Not Included. That was an adorable movie.
I love that movie.
I don't think I've ever heard of it.
Batteries Not Included. It's probably on Netflix, but if not, it probably costs like $1 to rent because it's old and didn't make a ton of money, but it's adorable.
Okay.
You know what else I haven't seen in a long time that I loved when I was a kid was Cocoon.
Yeah, those came out at about the same time, I would think.
Yeah, probably. I'm aging myself there.
Sometime in the 80s, late 80s, Steve Gutenberg kind of stuff. Yeah, wait, there were 2 people, and that's actually the husband and wife, the old couple from the Batteries Not Included movie, were also in Cocoon.
Yeah, I think so.
Yeah. Jessica Tandy and I can't remember her husband's name.
Well, and on that same subject, there's Short Circuit too.
Oh yeah, we actually just watched that like 2 weeks ago. It was great.
That's a good one.
It's funny because they filmed it in Astoria, so like recognize things.
Yeah, my kids like all those movies.
Did you guys understand what the difference between a fuel cell vehicle and a battery powered vehicle was? The cool thing about a fuel cell vehicle is it does pretty much the exact same thing that a battery does, except it uses a gas, most likely hydrogen gas. And so what is one thing that people do not like about electric cars?
They don't have a lot of power.
No, that would be incorrect. They have. Have you seen any of
I've
the?
never driven one.
There's some pretty awesome videos of like Teslas chained to the back of like a huge, 350 pickup truck, and they fight, and the Tesla wins every time.
Yeah, I can see that. I know people like Teslas.
Generally, the most common complaint is it takes the battery a long time to recharge. So the difference between electric cars and fuel cell vehicles is the fuel cell vehicles use hydrogen gas. So you could just pull up to a gas station, and they have these in the United States, and fill your car up with hydrogen gas. And then the process is super easy. Inside the car, you've got hydrogen gas, and then you've got oxygen gas from the atmosphere, and your product is good old water, and then a whole bunch of energy. So instead of producing a bunch of heat from this, the electrons that are going from the hydrogens to the oxygens, they make them go through the car's motor before they get over to the oxygen. The tough thing about the fuel cell cars is there needs to be a membrane that separates the oxygen and the hydrogen, and we haven't done a great job of making those things last a very long time. We're still in the process of making them better. And then the other issue is, where do we get the hydrogen from? Does anybody know where we get hydrogen gas from? The exact same reaction, but written backwards. So if this reaction up here gives you energy, then the opposite reaction takes energy, takes the same amount of energy that you would have gotten from causing the first reaction. So this is the oxidation or the combustion of hydrogen gas. And down here, I'm taking a water molecule and separating into hydrogen and oxygen. And to do this, we run electricity through the water. And when that happens, then the hydrogen gets their oxygen or electrons back and it turns into hydrogen gas. And then the oxygen lost the electrons, so it turns back into oxygen gas. So where do we get the electricity to make this happen? The easiest way to do this is if this electricity came from solar. So all day you could have solar panels just disassembling water molecules and then using that hydrogen to create the fuel that you would use for your fuel cell vehicle or for your electric generating plant, and while the sun's down. And then the next day, then it makes water, and then the next day you disassemble those water molecules again. So it would just be a closed loop of hydrogen and oxygen and water molecules. And so the byproduct that came out of your exhaust at in your car or on your at your electric plant would literally just be water molecules. People aren't going to be upset with that.
So why don't they put solar panels on the electric cars then?
The solar panels can't charge the car as fast as the car dissipates the electricity.
Okay.
Yeah, you can see this reaction on page 350. Sorry, what were you saying?
I'm just saying it seems like if someone wanted to build a fuel cell vehicle, that would probably have to be a hybrid between fuel cell and electric, so that you could use the just kind of go back and forth, but I'm not exactly sure how that would work. So.
Let's see. So it looks like can you see this wiki page?
It's loading. There it is.
So it looks like Toyota has created a model in 2015 called the Miria, and so that you would just pump hydrogen gas into there and then water vapor would come out of the back of the tailpipe. Looks like Honda has one, Hyundai has one, Toyota made some buses. That's really funny. There's a hydrogen powered bicycle. Looks like GM and has made some stuff for the military, and there's a Chevrolet Colorado that's hydrogen powered. That's interesting. Airplane, hydrogen powered. Okay. Okay. So they're out there. The main problem with this would be there aren't a lot of gas stations that are selling hydrogen gas. I'm not really sure how many hydrogen fueling stations that there are. There's a there's obviously a lot of electric charging stations, not as many as gas stations, but you see them all over the place, like the parking lot across from Full Sail or across from the movie theater. There are some Tesla charging stations back there.
Is that in the river or Dallas?
That's in Hood River.
There's a place we stay at in Florence that the actual hotel has like an entire row of just Tesla chargers and then another row of, electric car chargers.
Gotcha. I just looked up the hydrogen retailers, and it just looks like they're only in California. There's a whole bunch in the Bay Area, and there's a whole bunch around Los Angeles, and there's a couple in Sacramento, and then one near, not far from Reno. But I'm not seeing
It's
them
not that surprising.
anyplace else. There are none in Parkdale. The closest one is 427 miles away.
So don't go buying a hydrogen car unless you're planning on moving to California.
Ooh, there's one in Toronto. Even further away. Okay. So I think that's all I got today. I'll talk to you guys on Wednesday.
Okay.
All right.
Bye.
Have a good night.